morning, everyone, and thank you for joining us for this first of a series of webinars from Massons Healthcare on digital and 3D printing technology. My name is Bill Marmaris. I'm the Education Manager here at Massons Healthcare. And this morning we have Nick Scoville, our 3D print technician here at Massons Healthcare, and also Simon Bartlett, who's an application engineer with Evoke 3D, presenting on materials for 3D printing in orthotics and prosthetics. So in a moment, I'll pass over to Simon. He'll tell us a little bit more about Evoke and his role within Evoke. I will ask you all to keep microphones muted and cameras off. Please pop any questions in the chat section and we'll address those at the end of the webinar. This webinar is also being recorded and we'll make that recording available in approximately a week from today for those that missed or need to review the material in the webinar. So at this point, I will pass over to Simon.
Thanks, Bill, and thanks, Massons, for the opportunity too. A little bit about myself. Simon Bartlett, I'm a mechanical engineer by trade. Worked predominantly in the automotive industry for 10 odd years and started 3D printing and started my own business about 25 years ago now. And so worked with multiple sort of technologies. But my key role or my main role during that time is to be a facilitator, is to sort of help individuals or companies to take applications or take ideas to market with using additive manufacturing. Yeah, so my role within Evoke is just that, is working with potential machine buyers to look at, I guess, to make sure that their application makes sense. But Evoke itself is a supplier of end-to-end solutions for additive manufacturing. So we do software with the likes of Entopology for digital workflows. We are the sole agent for Australia and New Zealand for MJF, for HP technology, and then post-processing as well. We've got multiple technologies for vapor smoothing, which Nick will talk about, but also forms of mechanical finishing too. And all of that too, something which we rely or we put a lot of effort into is servicing as well. So making sure, as a machine owner myself and a business owner, I know the pain and the costs that machine downtime causes. So we spend a lot of time making sure that servicing is at the front of everything that we do as well. So the agenda for today, what I'll be covering, and I'll do my best to try and make the science of materials somewhat interesting. I know from historically I slept through a lot of lectures, but I'll try not to in this case. Going through the keys for adoption, because we always need to be mindful of why 3D, the classification of polymers and a little bit of material science. We'll go through very quickly the HP material portfolio, and then also, I guess, some of the work that I've been doing in this field and the materials, etc., surrounding O&P. So starting with keys to adoption. So the last thing we want to do is actually replicate what you're actually sort of doing now. So everything which we do when we talk about 3D, we need to think about value add. And the 5 key pillars to sort of value adding. So we talk about complexity. Remember, 3D printers are effectively a dumb machine. So they'll print anything that you've got. So part complexity does not, particularly with the HP technology, does not slow down or add print time. Part consolidation. So this is talking about doing more with less. So reducing part count. So anything which we can incorporate into the design to print it as a single piece makes sense. Again, because complexity coming for free. One of the key benefits too of 3D printing is being able to print on demand. So we're able to go from a push supply chain to a pull supply chain, and we can align with what production requirements are. The next one, enabling functionality. So remember too, we can add lightness. So we can use lattice structuring, etc. We can make areas thin or thick. So we have the ability to tune a part depending on the end requirements. And particularly, I guess, relevant to what we do in I&P is this personalisation and customisation. So every part we produce is different. So it's always pertinent to, when you are looking at adoption, to make sure that, as I said, you're not just replicating what you're doing now, but you are adding value. And the more of these boxes that you can tick along the way, the more benefit that you're able to bring by going to and moving towards 3D. Okay, the heavy part of today is talking about the material science. So we're talking about polymers. And so polymers, for anyone that's versed in their Latin, polymer is broken up into two. So poly meaning many and mer meaning units. Okay, so, and this is when we talk about polymer chains is actually a link of multiple mer or multiple units. Okay, so then we break that down from polymers, plastics, into thermoplastics, thermosets, and elastomers. And then we can break thermoplastics down even further, and this is where we want to focus today, into semi-crystalline and amorphous. So semi-crystalline examples of that are, nylon, polyester, polypropylene, where amorphous materials are more your ABS, polystyrene, polycarbonates. So, and we'll go down a little deeper about the differences between those two as well. And then over to our right, we're also talking about elastomers, so TPUs. So the technology which Massons have here, specifically we're looking at semi-crystalline materials, and predominantly to that is the family of amides or polyamides, and also elastomers and TPUs. So again, the boring sort of slides, but it's interesting to note that the images that you see there really do help to dictate or help to characterize some of the attributes of the materials. So for an amorphous material, if you imagine, it's a random bunch of polymer chains. Okay, now one of the things to note, and one of the key differences, is that amorphous materials don't have a specific or a defined melting point. So they go soft and they flow, whereas with crystalline materials, we do have a very, very defined melting point and glass transition temperature. Some of the other things too, differences in terms of ductility and strength. Amorphous materials have a tendency of having lower chemical resistance, and they're quite often transparent too. Whereas on the other side, our crystalline and semi-crystalline materials, so we're now talking about these polymer chains, are a lot more uniform, a lot more ordered. Now, as I said, they have and what is unique, they have a very good or a very controllable window of their melt point. They have a lot higher strength and stiffness and wear resistance, higher in chemical resistance as well, and they're generally opaque. And the reason for that is so any light which comes into or hits a semi-crystalline material, is the light is actually scattered within the part. Whereas for amorphous materials, the light is able to flow through the part itself. And just going into that a little bit deeper. So, and as I said, it's mindful of just remembering those graphics of the polymer chains as well. So amorphous materials like ABS, etc., ASA is another one, is they have a tendency to shatter. So, and that makes sense too. If you imagine those polymer chains, when I'm applying a load, the load or the crack as it propagates is going to go through those polymer chains to find those weakest links. So that's why we get a shattering approach, as opposed to a semi-crystalline material like a nylon. And we've got a gear there. Nylons are used extensively for gears. Is we have a very defined crack propagation. And that's also sort of shown in that tensile test bar there. So the crack actually propagates along that controlled or along that ordered structure. And just briefly too, when we're looking at amorphous and crystalline materials, it's also important to sort of think about their processing and obviously their cost as well. So the envelope in regards to cost for HP and powder bed technologies is we play around with a lot of the polyamides, and you can see there. So they're around about those melting points around 150, 180, those sintering temperatures. Whereas on the other side, for a lot of our amorphous materials, so our ABSs, as you can see, they're PMMA, etc. So they are more of a commodity material, and they have lower melting points, etc. Now, this is where it gets one of the things to remember was on with the earlier slides when we talked about having a very definitive or a very defined melting point. And this is why we have to use, or why we do use, semi-crystalline materials in powder bed technology. So, for instance, the optimum operating window for a polypropylene material in the HP technology, that window is only plus or minus 1 degree. So we're talking about around 180 degrees, plus or minus 1 degree, makes the difference between able to print apart and not print apart. So being able to have a very defined melting point is critical for that to work. Now, that's not to say that powder bed technologies can't move up this pyramid, and they can print in some of the peaks and some of the PEG materials. And you can also, FDM is very common as well for a lot of the ABSs and can also do peak. But what comes with that too is machine complexity. So if we need to have an operating envelope of around 300 degrees, that becomes a lot harder to A, control, but B, it makes the hardware itself a lot more expensive. So we have this rationale to use more of these commodity type materials, not only because they have a greater number of applications, but also too, it influences the design of the hardware. All right, so having a quick look at time. So in regards to the material portfolio that HP has on their technology, so we have a range of polyamides, and you can see they're PA11s and 12s, etc. We have polypropylene. We also have a white material now as well. So which material you would end up using really comes back to the application. And so we'll dive deeper into that as well. So as well as the polyamides, we have a flame retardant polyamide as well. We also have a TPU and a TPA, so more of a flexible material. The TPU is a standard of around about 92 Shore A, which can sound rather stiff, but with 3D printing, you are able to design different sort of lattice structures, etc. So even though you start with one particular hardness, you can actually control and modulate the flexibility based on maybe a unit cell structure, which is similar if you look on the image to the second right of a midsole. If we change that unit cell size, we can actually vary the cushioning effect that we see in a shoe. And then when we talk about control and what we do have with the HP technology, we can control a number of attributes in terms of both temperature and agents predominantly to give us different not only mechanical properties but physical properties too. So looking at let's say for instance electrostatic discharge, so we can vary the amount of carbon which we're effectively putting into the part, which allows us being able to dissipate, a build-up of static, as an example. But this is where we now start to sort of get into, the nitty-gritty, so to speak. And what I, as an engineer, what we typically term as death by data sheets. Look, every material supplier, every hardware supplier will be able to give you a telephone book of data sheets, but really the key is trying to digest all these materials and understanding what they actually mean. And this is where what I would suggest, one of the key sort of takeaways from today is, yes, data sheets are great, but it's actually understanding what's happening behind those data sheets. And this is where we look at stress strain curves. And this is where I'm hoping it's not getting too heavy for a Thursday morning. So if we're looking at, for instance, an AFO, now what we really want to do is that region that you see in blue on the stress strain curve, this is what we call our elastic region. So any force or a force which is applied, as long as it deforms the AFO, as long as it deforms it within this elastic region determined by the mechanical properties of the material, it will, when the load is taken away, that force is taken away, it will go back to its original shape. So this is where we want to be in terms of and thinking about if anything's got to flex or be stressed, etc. Now, as soon as you go past that elastic limit, that yield point, this is where we do permanent deformation, and so what we call our plastic region. So the more time you spend here, whether we're, depending on how far into this region we go, we're now starting to effectively cold work, or we're starting, stress and crack propagation. So fatigue is what we're starting to play with, ultimately to a point where you get the ultimate tensile strength, where it starts to break, and the fracture point. So when you're thinking about your data sheets, it's mindful of, or you should just think about this stress strain curve and where you want to be, and the playground or the sandpit of where your part needs to sit. Because as I said, you want to make sure that you're effectively within that elastic region, because as soon as you go over that tipping point, this is where you cause, basically, this is where we go back to that image of the fracture mechanics. So how then it becomes important to think about how the part potentially may fail. So this is probably one of the key takeaways I'd sort of say from this morning. And one of the other sort of things that it's worth talking about, which I'll just briefly touch on as well, is this is the death by data sheet before, yeah. So we've got all of our mechanical properties for all of the HP or powder bed fusion technology, the polyamides. Then on the right-hand side, I just want to show you an example from, FDM, because I know that, a lot of people, tuning in this morning, they'll have FDM machines in their workshops. Now, what is of particular note from this data is that with the HP technology and powder bed fusion technologies, you get very close or the same materials in X, Y, and Z. So that's what we call being isotropic. Whereas if you look at the FDM material, depending on the build orientation, whether it's in X or Y or in Z, you've seen there a 30% drop off in terms of tensile strength. But then also too, if you look at the elongation of break and at yield, you see quite a dramatic difference as well. It's actually lower, but a dramatic difference between the direction that the part is that is printed, which becomes a lot more important, particularly when you're producing something like an AFO, where build orientation really can have a dramatic effect on the way that the part is going to perform. But what does all this mean? And so again, mechanical engineer here, I'm not a clinician. So how do I sort of, on my day-to-day, when I'm working with, let's say, with an AFO, what does this mean for me? So I actually start on the right-hand side. So one of the things that they've spent a lot of time on is building up what we call a finite element analysis, or the model. And effectively what that is once we draw something in CAD, we wrap a mesh around it. And with that mesh, we're able to apply basically this stress strain curve. We are able to apply at every node at that mesh. Okay, and so what we do then is we plug in the loads, which are loads to simulate, load bearing and weight, and then we're effectively stressing the part. And so the area which is then highlighted there, as we know, this is an area which is common to what we call frog mouthing. And if you look at the colour map that you see there, some of those areas which are then shown in red, what we try and do is make sure that those areas of stress are actually below what we see on our data sheet. So it's having this sort of balance between the two and making sure that anything that we see on the data sheet then is actually only going to stress the part within that elastic region. And then what we can do is, basically with the help of, clinicians, etc., we try and absorb and understand what you're trying to achieve in terms of design, and then apply that design into our FEA model. And then we have this feedback loop to ensure that it's giving your patients exactly what they need to do or what you want that part to achieve. And then we make sure, and we're backwards from that to make sure that then the part is actually going to perform over time within that elastic limit. So over the course and life of the part, that it actually behaves the way that you want it to. Now, one of the other things, and the last point in this too, like post-processing can actually have a function to play here in what we do or how we can actually change the mechanical performance of the material as well. And this is where post-processing, like using the AMT system, can actually have a benefit in terms of the Young's modulus or that these stress strain curves and actually improve on the mechanical performance of the part. And with that, if you want to know more about what I was just talking about there, I'm actually at the presenting at DAOPA later this year, between the 16th and the 18th of October, and just talking about having this feedback loop and testing, etc. And for now, I can hand over to Nick, and Nick will be talking more about the AMT process. But I appreciate your time and thank you.
Hello, everybody. Thank you for joining. My name is Nick. I'm one of the 3D print technicians here at Massons. Let's go to the next slide here. Yeah, and I've been with Massons for 4 years and was previously with the Autobach US IFAB team, helping them to develop their cranial remolding program. So I want to take a second to thank Simon for his detailed knowledge of all the different materials that we use here for MJF. Your attention to detail and data are always appreciated. So I want to take the last part of this webinar to talk about an important step in the additive manufacturing process, and that is vapor smoothing. Vapor smoothing is one of the tools that we have in our tool belt to produce high quality 3D printed parts, and we utilize it to create a superior finish that is more watertight, it's food safe, it reduces bacterial growth, and it creates a surface that is smooth to the touch and easy to clean. And it is also stronger, specifically regarding tear strength, which I'll get into more here in a minute. So vapor smoothing is a condensation-based process, and it turns 3D printed parts into smoother, more functional finished components. In a lot of cases, 3D printed parts are not end-use ready when they come off the printer. They can have a rough and porous surface that requires post-processing to make them end-use ready. After being put through the vapor smoothing process, the parts will be, as the name implies, they will be smoother, less porous, and they will look like an injection molded part. Let me get back to that slide right there. And yeah, this process provides the finishing touch to parts in the additive manufacturing chain. Here at Massons, we do print in 2 different materials with 2 very different properties and requirements when it comes to vapor smoothing. First one that we print in is TPU. It is a rubber-like material that is very similar to flexible thermoplastics that we've used in OMP for years. It is the material that we print with that requires vapor smoothing to achieve what's known as optimal tear strength. So what is tear strength? Tear strength is also known as tear resistance, and it simply measures a material's ability to withstand tearing forces. And in our typical applications here in the OMP industry, it's an important factor to take into consideration since devices in our field are really known for taking a beating. The other material that we print in is PA11, and it is a high-performance thermoplastic derived from castor beans, known for its excellent mechanical properties, impact resistance, and its bio-based source. Unlike some other polymers, PA11 is known for its flexibility, making it ideal for parts like hinges, springs, or in our cases, AFOs and prosthetic devices. So how does the vapor smoothing process work? During this initial step of part conditioning, during this initial step, the parts are conditioned in the process chamber to ensure they reach optimum processing conditions. This includes pressure, heat, and solvent amount. During the processing stage, the vaporized consumable is injected into the processing chamber, evenly smoothing part surface under highly controlled conditions. These are the 3 factors that we can change to fine-tune the recipes that we process parts with. During the curing stage, the parts are then cured and the consumable is removed from the surface of the part, causing it to re-solidify, and this completes the smoothing process. Only after drying. Drying can take 1 to 2 hours, and during this stage, it ensures that no residual consumable remains on the material, and the part is now ready for end-use application. All right, so a few things that I just wanted to chat about really quickly when it comes to designing for vapor smoothing. variable thickness parts, through holes, thin wall warping, and how to hang parts in the machine. So variable thickness parts, the parts that we tend to design in this industry, they do require different thicknesses to achieve different outcomes. While we can achieve great results with variable thickness parts, we should try to design smooth transitions between the different thicknesses. What you see in the image above is what's known as bridging, and this can happen where two different geometries meet at a 90-degree angle. Next design consideration to take into account is through holes. A through hole is any opening that allows air to pass through the part. In this process, allowing the vapor to pass through a part will ensure the chemical is able to reach all sides and evenly smooth the part. Prosthetic liners are a great example of what's known as a blind hole. In most cases, there is a cup at the distal end of the socket, which makes it difficult for the vapor to evenly smooth the parts. This is unavoidable in some cases, and steps can be taken on our end to achieve the best result, which we will always do, but know that it is possible for the device to smooth on the outside more than the inside in these cases. Liners that have a hole for air expulsion or a large disc-like component, distal component, are best suited for this process. Another thing to take into account is thin wall warping. So the wall thickness for vapor smoothing is very similar to what HP recommends for MJF printing, and that is 0.3 millimeters in the XY plane and 0.5 in the Z direction. Going below those numbers can result in warping surfaces. Hanging parts in the machine. So your parts will be hung in the best orientation for optimal smoothing, but witness marks, which I'll show on the next slide, are possible. Those can be avoided if you do want to design a sacrificial hook that would be removed after the fact. This material does clean up well, it buffs very well, it heats very well. Here are a few examples of how we hang parts, as well as the witness marks that can possibly show up through the vapor smoothing process. You'll see that on that middle picture there. The far right picture shows the trays that we hang parts from. Notice that the AFO devices in this picture are hung at a skewed orientation. That's something that we have to do on our end in order to achieve optimal results. So this is key to achieving consistent smoothings. And yeah, we will always try to hang your parts in the best possible orientation. That's not something that you have to dictate towards us. And so yeah, do you need to smooth your parts? It does depend on the material and the application. TPU requires vapor smoothing to achieve optimal tear strength. PA11 devices, on the other hand, can be delivered non-smooth, but they will quickly attract oils, grease, as well as dust. If gluing on a covering is the plan, then we do recommend not smoothing the part, and this is the case with most foot orthotics. And that'll wrap up my information on vapor smoothing. If you do have any other questions, feel free to reach out, and I will hand over to Bill for closing up.
Okay, thank you, Simon, and thank you, Nick, for that informative presentation on materials and vapor smoothing. And keep in mind, this is the first of a series of webinars. So over the next few weeks, we will be having these 30-minute webinars, and you see the schedule there. So some practical tips for improving your scanning. So whether you're new to scanning or have been scanning for some time and just need some tips to improve scanning efficiency, that'll be worthwhile information. Building a CAD/CAM service model, and that'll bring everything together in one session. So if you're looking at starting out in CAD/CAM or starting a new business and want to implement CAD/CAM from the get-go, that'll be valuable. And then we'll wrap up this series of digital webinars by having a look at some software systems that will allow you to design 3D O&P devices.
There's just been a question come in from Rod, that's all, in the chat, which is just about testing elastic regions of the orthoses. Is it done by mesh analysis? So that might be something for Nick and Simon to answer for us. And also, does the drying from the smoothing remove all the chemicals? And if so, what does the part smell for? Why does the part smell for so long after delivery? And the other one was just about what files we can take, or what files, if we receive them, can we use for 3D printing?
Yeah. Short answer is yes. Look, there's a number of different ways you can do it. I mean, I guess traditionally it's been suck it and see, but I guess this is where well, I guess one of the beauties is having a digital workflow is that you can do things like this. So the way that I use it and work with clinicians is to obviously try and understand what they're trying to achieve and put that into some form of sort of standardized sort of design, and then we can run it through that mesh analysis. I guess the key for that is we don't want to do it for every clinic, for every patient, etc. And this is where it comes into what I was going to talk about with at AOPA, is we want to come down to a pretty sort of finalised design, which accounts for 80% of effectively the population, and then that's what we test, and then the design attributes from that 80th sort of percentile. We actually use that in every design after that. So we generally, what we do is we test one to an optimum design, and then I guess having this feedback loop, we always look to improve on that design, to then look at those elastic regions, etc. So short answer is yes, we can do it as long as you've got a file that's been digitized. We can definitely do it, but then, as I said, so what we try and do is to have a standardized design. So, and then everything, those design attributes are then common across every AFO that we do for that particular clinician. So I'm hoping that answers your question. But yeah, so as long as we have a digitized file, we can run basically runs a mesh, and then we can do what we do is finite element analysis. So yeah, happy to, if you've got my email was there, or contact Nick, and yeah, happy to go through it in more depth, or otherwise check into talking at AOPA in a couple of weeks as well.
Yeah, and I'll just jump in real quick just to answer the question about the vapor smoothing. You will find when you receive parts from us that have been vapor smooth, they typically are coming out of the smoother, and we're sending them off within a day or two. It does take about a week to a month, depending on the part and the geometries, for that kind of residual smell to go away. And it's a lot like if you use epoxy resin. Epoxy resin, it's going to continue to smell for upwards of a week to a month. But that does not mean that it's not food safe at that point. From the time that it comes out of the vapor smoother, those parts are food safe and skin safe. And file wise, just to address that, yeah, STLs, OBJs, 3MFs, really anything that comes from an open source formatting, as well as if you do use the Massons app, you will send that to us and we can convert those. But yeah, we basically take anything that's open source. No other questions. I think that'll wrap us up, and hopefully we will see all of you back here next Thursday for the next round of 3D printing learning.